very much. I hope that everybody can hear me. Please let me know. I suppose so. So my name is Helga Lippmaa, and the talk is called Polymath Grot 16 is not the limit. Because it seems that almost 50 talks in this conference are, sorry, I see a chat. Okay, yes, we can hear. Because already 50 talks in this conference are about zero knowledge, I'm not going to introduce the topic much. I'm just going to mention that in the case of ZK SNARKs, you usually have a description of some computation F that is public. Then you have a public input or statement X, and then the prover has a private input or witness W. And then in the non-interactive setting, you essentially always have a trusted third party who generates a structured reference string and sends it both to the prover and the verifier. The prover applies the computation to the private input and public input, and then adds to this a proof that the computation was done correctly. And as usually in the case of zero knowledge, we have the properties of completeness, knowledge soundness, zero knowledge. But what makes SNARK special is that you also have a built-in efficiency requirement, namely you want the proof to be as short as possible, and you want also the verifier to be very, very efficient. So when we look at the landscape of current efficient SNARKs, we basically have two categories. We have one category, those are the SNARKs that are good for prover. This includes mostly, but not only, hash-based SNARKs like Fry or tensor code-based ones like Pinius. It also includes GKR. And then you have good for verifier SNARKs. This includes Grot 16, Plonk, and several others. And those SNARKs are usually based on elliptic curves on bearings. So one question is like, what happens if you want both the prover and verifier to be efficient? And there doesn't seem to be really like some magic wand for this. What people very often do in practice is that they compose a SNARK that is good for a prover with a SNARK that is good for a verifier. And the compositions that I've seen in practice are like JKR plus Grot 16, breakdown plus Grot 16, Fry plus Grot 16, etc., etc. So you see the pattern, it's almost always Grot 16. And in particular, there has been a huge progress in the ZK SNARK land in the last 5 years, like really a scientific revolution. But Grot 16 still lands supreme after 8 years. It has the shortest argument and it has the fastest verifier. Before going to explain Grot 16 and what we did in this paper, let me just explain pairings, or mostly like the notation that we are going to use. So in the case of pairings, you have like a bilinear group that consists of a large prime P. You have 3 groups, 2 source groups and a target group that all have prime order P, and they are additive for the purpose of this talk. Then you have generators of G1 and G2. And then you have a pairing, which is a bilinear map from G1 times G2 to GT. The bilinearity means, yeah, it's bilinear. So it's A sub 1, comma B sub 2 gives you A times B sub T. One thing that is very important to know when you actually do pairings in practice is that the efficiency of all operations depends on the curve that you're going to use. So in the case of 128-bit security, the industry standard curve at this moment is PLS 12381. And in this case, the finite field elements are 256-bit long, G1 elements are 384-bit long, and G2 elements are 768-bit long. So notice that the G2 elements are twice longer. This gets even worse in the higher security level. So for example, if you go to 192-bit security level, then the field elements still have the same length, but the length of G1 elements has increased, and the G2 elements have 4 times longer, are 4 times longer than G1 elements. So after that, let's just have a very bird's eye view of CROT16. I'm not going to describe any details, just the syntax of the protocol. So in this case, the SRS depends on the computation, so it's a non-universal SNARK. The argument consists of only 3 group elements, and notice that there are 2 elements from group 1 and 1 element p sub 2 is from group 2. And as a verifier is extremely efficient, verifier just executes 3 pairings and like a number of group operations that is linear in the size of the public input. So because CROT16 is so nice, it would be good to understand how optimal it is. So it has, the argument size is 3 group elements, and also in his original paper, Jens proved a lower bound, saying that at least 2 group elements are needed. And one of them has to be in G2. And we also know that if we use a different arithmetization, we can actually have 2 group elements. So we actually need this lower bound. So what is this different arithmetization? It's something that is called SAP, Square Arithmetic Programming, instead of R1CS. But the problem in this case is that one uses symmetric pairings. And in the case of symmetric pairings, the group elements are considerably longer. So while you only use 2 group elements, bitwise you suffer. So this is actually not a good solution because the argument is going to be longer than in the case of CROT16. Also, one thing to notice is that CROT's lower bound works in the standard model. So it only talks about group elements. It doesn't say anything about field elements. And more importantly, to the current talk, it talks about the number of group elements. It doesn't talk about bit length. Okay, so let me try to give a scenic route to our construction polymath. And I'm going to give like a high-level intuition what polymath does differently compared to CROT16. But unfortunately, I'm going to assume at least some familiarity with CROT16. So as we saw, the main problem is that the G2 elements are super long. So one thing that we could try to do is that instead of having this p sub 2, we could try to transfer this element to group 1. So to have sig p sub 1, because this would be 2 or 4 times shorter. But the question is how. And here we can note that CROT16 uses pairings to do quadratic checks on the group elements. But another well-known way of doing quadratic checks is by using some kind of a commitment scheme, like the seminal KZG polynomial commitment scheme. Then you can think of this p sub 1 of being a polynomial commitment. You can open this commitment to a field element, and then you can do quadratic checks by using this field element. So that's the first major observation here. And KZG opening is shorter than a single J2 element, namely, like the opening is a field element B power, and the G1 element, which is like an opening proof, H1. But the problem with this easy solution is that we still have B1 in the argument. So the argument will have both B1, the field element, and this opening proof, which is another group element. And when you add everything together in 128-bit level, you didn't actually gain anything. It's going to be longer than one P2 element. Interestingly enough, in 192-bit level, you already now have a shorter argument. So the next step is that you can use the already mentioned arithmetization SAP instead of R1CS. So this is kind of like very symmetric arithmetization, and in this case, P1 is equal to A1. So this means that you don't have to transfer P1. So now you get actually proof that it's already shorter. So the cost of this is that you will have about twice bigger circuit, so the prover will be about twice slower. And the reason is that in this SAP, you don't have multiplication gates, only squaring gates. So that is solved. Now we are actually already syntactically, we already have polymath proof. But talking semantically, we still have several problems. The first one is that Prot16 has 5 trapdoors, and KZG is a univariate polynomial commitment scheme, so it works in the case when you have 1 trapdoor. We could use a multivariate commitment scheme, polynomial commitment scheme, but multivariate polynomial commitment schemes have longer proofs. So we want to stick with KZG. So the next step to do is univariatization, where we basically replace, we could, like, that's the first idea, we could replace each trapdoor with a power of a single trapdoor, x. So I is I is a small integer and x is a single trapdoor. So each trapdoor is x to I. I use the same idea in PKC 22, and in particular in that paper I used exhaustive search to find optimal i's that would give a good efficiency, but still result in a sound SNARK. Still, the problem after this step is that even after exhaustive search, the exponents I are quite large. And this having large exponents means that the polynomials that we're talking about have a large degree. And KZG prover time is at least linear in polynomial degree, which results in high prover complexity. To solve this problem, we make the following observations. First one is something that is trivial when you already know what is going on. Namely, SAP is a simpler arithmetization, and you can build Prot16 for SAP that has already -1 trapdoor. Observation 2 is much less trivial. It's related to this fact that if you look at the construction of Prot16, then 1 trapdoor is only needed to mask SRS elements corresponding to the public input. So we are kind of looking for a way now to remove this trapdoor too. And we do it by using a quite different verification algorithm, getting rid of this one more trapdoor. Very bonus, very positive side effect is that verifier actually becomes faster because of that. So not only we get rid of one trapdoor, but we have a faster verifier than Prot16. So basically, in polymath, verifier interpolates a polynomial in the finite field that has a degree that is linear in the input size, while in Prot16, you do like a long multiscalar multiplication that is as long as the input string. So at this moment, we only have 3 trapdoors, and when you have less trapdoors, it's easier to choose good ones. So we replace 2 trapdoors with y to alpha and y to gamma, where y is x to sigma. Here, x is a real trapdoor, alpha, gamma, sigma are field elements. And as in PKC 22 paper, we use exhaustive search to find small exponents that result in knowledge sounds. This exhaustive search basically recommended to use the following setting: alpha is equal to 3, gamma is equal to -5, and sigma is equal to n plus 3, where n is the circuit size. And now we are almost there, but we still have the final final problem, namely the structured reference string is circuit dependent, which means that it lacks some degrees of the monomial, which means that this SRS is not sufficient to be able to compute the KZG opening proof. And for this, we do the last step, which is we add another tractor that is only used to compute KZG opening. And this adds some elements to the SRS, but it doesn't make the rest of the argument less efficient. And that's it. That's profit. I have a long slide about the security proof. So completeness and zero knowledge proofs are short and standard. That is not the problem at all. The problem is in the soundness proof. The soundness proof is 7 pages. So first of all, CROT16 itself has a complicated proof. Now, because we replace independent random variables with the power of a single variable x, this complicates the proof a lot. Then to get tight security after Fiat-Shamir, we prove special soundness, which makes it a bit longer. And then finally, our proof is in AGM, algebraic group model with oblivious sampling. As we showed in the DCC 23 paper, KZG is often used strongly. It's basically used in pure AGM, where oblivious sampling is disallowed. While oblivious sampling is actually for free in most of the proofs. And part of the proof is machine check. 7 pages is a bit too long for me to write a complete, like, lean proof. So final words. This is a first improvement on CROT16 since 2016. So 8 years, long time, given the revolution in SNARKs. And hopefully this encourages other researchers to improve CROT16 even further. Actually, there's a recent e-print by other people trying to doing that, exactly that. The pros of our solution are that we have smaller arguments, which is even more prominent in the higher security level. We don't have any adversarially created G2 elements, which is good for patching. Verifier is potentially faster for a short public input and definitely faster for a long public input. And then the solution has some cons compared to CROT16, but those are mostly mitigated in, like, let's say, specific application area of SNARK composition. So prover is slower, but if it's used as a final SNARK, this is okay because the initial SNARK makes the state or this computation shorter, so the final SNARK the prover has less work to do. And then Polymath uses random oracle model, which is, I think, also fine because any known reasonable initial SNARK in SNARK composition already uses random oracle. So thank you very much, and I'm open for questions.
So please come up to the mic if you have a quick question while the next speaker sets up. Okay, then maybe I will ask a quick question. Now that CROT16 is no longer the limit, what do you think? What do you think is the new limit for proof size? And can you prove any lower bounds in a new model?
I haven't proven anything, and I don't have a good intuition in the case of random oracle model. My feeling is that maybe having 2 group elements and 1 field element is a strict lower limit, but maybe you need more. But this is just hand waving. I really haven't had time to think about it.
Hi. Can you elaborate on the machine check part of the security proof? So you said that the security proof, soundness proof is machine check.
So yes, so part of the, let's say, a lot of the proof is very long, but it's very, very standard. So you do just the usual, like, idealized group model proof. But then at some moment, when you have to, when you choose the exponents, you have to make sure that when you do the soundness proof, then the powers that shouldn't like collapse, they actually don't collapse. So you have to make sure that all the certain powers of exponents in certain polynomial expressions are all different. And this part is machine checked.
Okay, thanks.
Thank you.
Thanks. So we'll move on to the next talk of the session, which is field agnostic SNARKs from Expand Accumulate Codes. And this will be presented by Alex Block. Please go ahead.
Can everyone hear me? Okay, good. Thank you for the introduction. Yes, this is joint work with Zhang Fang, John Katz, Justin Feller, Hendrik Walder, and Yupeng Zhang. Of course, the topic of today is SNARKs, succinct non-interactive arguments of knowledge. I'm sure most of us here know what this means, but for brevity, it allows a verifier to ask a prover to say, hey, is this X in the some fixed NP language? And the prover will send a single proof, pi, and the verifier can look at this and accept or reject. We want all these standard properties: completeness, soundness, knowledge soundness, and of course, succinctness. Now, fortunately for us, there are a plethora of ways to build concretely efficient SNARKs. As I shamelessly steal this picture from Justin's book, we really have two lines of work. We have linear PCP-based plus pairing-based cryptography, which culminated with Groth 16, and I guess now polymath after that talk. And now we have the other paradigm of polynomial interactive oracle proofs plus polynomial commitment schemes. And that's where we're going to be looking at today. And in particular, we're interested in the question of building code-based SNARKs, error-correcting code-based SNARKs, which falls under this branch here, IOP-based polynomial commitment schemes. So why do we care about code-based SNARKs? Well, they have a transparent setup. We need no trust when generating these. They are plausibly post-quantum secure. And they have really nice efficiency properties that are tied to the underlying efficiency properties of the code. And I'll talk more on this later. And in particular, like I said, they're built from the polynomial IOP plus polynomial commitment scheme paradigm. And you can actually break down a code-based SNARK into two components: exactly the IOP plus a code-based polynomial commitment scheme. So now we've taken the problem of constructing a code-based SNARK, and now all we need to do is construct a code-based polynomial commitment scheme, and then we get what we want. And fortunately for us, there is a nice construction of polynomial commitment schemes from any linear code. And we call this the Ligero breakdown PCS framework. And in fact, it came from an earlier work due to Bootle et al. And it's really a framework for polynomial commitment schemes where you can take your favorite linear error correcting code, plug it in, and it spits out a polynomial commitment scheme. And from prior work. And what are the pros of this? Well, it's really truly plug and play. You give me a nice error correcting code, it gives you a nice SNARK. It's a complete pipeline framework. And the SNARK properties, like I said, are directly linked to the code properties. The proving time is roughly equivalent to the encoding time. If the underlying code can be instantiated over any finite field, then the SNARK is what we call field agnostic. And the distance of the code, which I'll talk more about this later, which you want to be large. When it's large, it gives you smaller proof sizes for a fixed security parameter. There are some cons, of course. Asymptotically, the proofs are square root in size of the input statement. And prior work had some downsides, concretely large proofs and breakdown. This was also remedied by follow-up work, and I'll touch upon that. Or in the case of Ligero, it's quasi-linear time because it uses Reed-Solomon codes. And because it uses Reed-Solomon codes, it's not truly field agnostic. You need special finite fields where you can do FFTs and stuff like that. And it's just a fact that when you want to design and analyze new codes, it's difficult. Even taking old codes and looking at them in a new light can be difficult. And I'll briefly motivate why field agnostic is important. There are a lot of times in SNARK proving, we want to prove statements like this ECDSA signature is verified correctly. And if you can't operate over the native field of that computation, you can get very bad overheads trying to embed it in a larger finite field where you can do the computation. And there's even more to this, but this is just briefly some motivation for that. So what's a bird's eye view of our results? So we give a new code-based PCS from the recently proposed expand accumulate codes due to Boyle et al. At Crypto 2 years ago. And we do three things. One, we have an improved/different analysis of the binary EA code. And this comes from some classical coding theory techniques. And this lets us get better concrete parameters than the prior work. We then take this analysis that we did and extend it to arbitrary finite fields. And this answers an open problem of Boyle et al., where they conjectured that over finite fields, things should still be OK. And that's what we reasonably expect as well, and we show this. And we concretely have quasi-linear time encoding and concretely large minimum distance when we don't use terrible Stirling approximations. And finally, we implement the SNARK. We actually have an artifact available at this conference, and we do it in the breakdown Ligero framework. It is field agnostic. The proof size and verifier time are both comparable with breakdown, with only a 1.2x prover overhead, really taking advantage of, as we'll see, the simplicity of this expand accumulate code. So I've tricked you. I said this was a talk about SNARKs. It's actually an error correcting code talk. Thank you. But just for a brief comparison, asymptotically, we're as good as basefold for prover time. For proof size, we're exactly the same as breakdown because we're using their framework. But concretely, as you can see, we're faster than basefold. Our proofs are concretely smaller. And our verifier time, unsurprisingly, again, is comparable to breakdown, though slightly slower. All right, for the remainder of the talk, I'm just going to give you a quick overview on what error correcting codes are if you don't know, the EA code, which is central to our SNARK, and then this funny technique called IOWE for distance analysis, and then give a brief, very brief, very stressing, very brief overview of the finite field analysis, along with experimental results. So what's a linear error correcting code? Very simple. It's a little n dimensional subspace of f to the capital N, such that it satisfies this distance property where every non-zero element of the code has high Hamming weight, has Hamming weight at least d. And equivalently, C is actually a mapping defined by a full rank little n by capital N matrix. Okay. For codes, the parameters of interest are always the rate. We want this to be constant. When this is constant, that's the only way we can get truly linear time provers. And we want it to be a large constant approaching 1. The encoding time, this is also very important. We want this to be concretely efficient. So the time to compute this product, you could think this is the sparsity of the matrix G. You can think how structured is the matrix D to really take advantage of fast computations. And again, we need rate to be constant in order for this to be truly linear time like we want. And then the relative distance is the normal distance normalized by the output length of the code. And again, I'm stressing here, we want this to be large. As it approaches 1, we will get smaller proof sizes for a fixed security parameter. Okay. So what are expand accumulate codes? Boyle et al. Introduced these really simple class of codes. On the left side, you're going to have a random sparse matrix over a finite field. You have little n by capital N, it's like this little wide matrix. And intuitively, this matrix is what we call an expander. So any input to this matrix X is going to, with high probability, increase the Hamming weight of X on the output by a significant amount. And then on the right, it's this very, very simple matrix called the accumulator. The accumulator, as you can see, if you input a vector X and output a vector Y, the J symbol of Y is just the sum of the first J symbols of X. So even though this is like a dense matrix, it's linear time. It's very fast to compute this thing. Okay. And altogether, this is the expand accumulate code. So I've given you this deterministic part of the code. It's very simple to describe, and this randomized part. So naturally, how do you choose this randomized code? Okay. There are two ways, also both given in Boyle et al.'s work. One, and I've generalized this to any finite field, is you can think of a Bernoulli matrix where every element is sampled IID from this generalized Bernoulli distribution. And just as a sanity check, if F is binary, then this is exactly the Bernoulli distribution you know and love. And Boyle et al. Proved that the EA code in this setting for binary is asymptotically good. It has constant minimum distance, which they need for their applications, and is good for us as well. And it has logarithmic sparsities. So the probability is log n by n. So you can expect the matrix to have log n entries per row or column. And they conjectured the same for larger finite fields as well. They also give a second sampling procedure as a suggestion, which is like a fixed row weight. So you can think every row of the matrix is now sampled uniformly at random from this set of fixed weight vectors. Intuitively, this looks like a left bipartite random graph with edge weights in F, but I'm not going to get into that. And again, it was conjectured that this holds the distance is constant for logarithmic sparsity over finite fields. So what's our approach? We actually cheat a little bit. We take both of these matrices. We say on the left half, we're going to have this fixed matrix. On the right half, we're going to have this Bernoulli matrix. And this is going to be our expand accumulate code. It's going to be this kind of, we call it juxtaposed code. And we're going to take our rate again to be constant, because this is what we want for applications. And we're going to consider logarithmic sparsity. And what we show is that all this theorem says is that these codes are good. They're asymptotically good, so we have constant relative distance. And I'm not going to say what this constant is, because in this theorem it's quite bad. And with inverse polynomial probability. So when you sample this matrix, this E1, E2, with inverse 1 minus inverse polynomial probability, it's going to have constant relative distance, which is what we need for our applications. Some things to note. We really consider this juxtaposition thing because we had some limitations in our analysis. But I'm pretty confident you do not need to do this. I think you really don't need to do this. And it's more we need to sit down and redo the bound and figure it out. And again, also the parameters in this theorem are absolutely nowhere near tight. These come from very, very loose Stirling approximations. And they can definitely be tightened up, especially in the Boyle et al. Paper. They have a really nice case analysis where they can take advantage of different tighter Stirling approximations. So something like that can be applied here too. But for our purposes, this was enough for now. Okay, so how do we prove this? So what we're going to use is a technique from the coding theory literature called the IOWE technique. And it stands for input-output weighted enumerator. Okay, what the heck is that? So suppose I have a deterministic matrix first, and you can have your input x and your output y. Now think about, okay, if x has some fixed input weight and y has some fixed output weight, h, a natural question would be to ask, okay, how many vectors of weight w map to a vector of weight h? Okay. And this is what the IOWE is, the weight input-output weight enumerator. It exactly counts the number of vectors x of weight h that will map to a vector of weight, or sorry, input vectors of weight h that will map to an output vector of weight, input vector weight w, output vector weight h, sorry. Okay, why is this useful? Let's build up to how we use this in distance analysis. Suppose actually that, oh, it's actually distribution in front of here. It's not just in any input w, it's some uniform distribution of weight w vectors. Okay, now given this, you can now ask the question, what's the probability over choosing x from this set that the output is weight y, or a weight h? And that's exactly given by the IOWE, because it's counting exactly what you're looking for. How many vectors of weight w map to a vector of weight h, divided by the uniform probability. Here in this example, f is binary, but if f is a field of size q, then you have a q minus 1 to the w down here. Okay, one more step to getting distance analysis for the EA code. So how do we apply it here? So the EA code is two matrices, right? We have the random expander and we have the deterministic accumulator. You get your x, it outputs y after you apply E, then you feed y into the matrix A and you get some vector C. Now let's say vector C has weight h, vector y has weight w. How many vectors of weight w map to a vector of weight h? This is exactly the IOWE of the matrix A. Okay, so that's great. But notice that y actually comes from some distribution. E is a random matrix. So the output of this matrix you can think fits in some distribution. And what does this distribution look like? Well, if I consider a vector of weight r, I can define P sub rw to be the probability that a vector of weight r x maps to a vector of weight w. Okay, and for parameters that we choose, this probability, let's say, is very high when w is like r times log n at least, but not super important for this talk. The key thing here is, if you remember on the previous slide, I cared about when this was the uniform distribution over weight w vectors. Well, with both ways to choose the expander matrix, either via Bernoulli distribution or via this fixed weight row weight, you can show that, or you can argue that, if the output has weight w, then it's actually distributed like a uniform vector in the set of weight w vectors. Okay, so this gives us exactly the distance bound we want. So the binary distance analysis case breaks down to applying some union bound to here, and then what you get is this expression here. And this is exactly the expression we bound poorly in our paper to get the inverse polynomial probability. Okay, so but I haven't told you what this is. What is a sub wh? Well, fortunately for us, in the binary case, this is known from prior work. It looks like something like this binomial. You can show it via like a stars and bars type theorem. So, and again, this is the number of weight w vectors in F2 that map to a vector of weight h under the accumulator matrix. But it was not known when you change 2 to any q. And this is the main technical lemma of our work. We show it's this horrible expression. It's 3 binomials, 2 exponentials, and a sum over I equals 0 to w. And you can kind of check when q is equal to 2, it actually exactly equals this expression up here. So the IOWE of the accumulator matrix over FQ is this horrible expression. Fine, it's horrible, but we can still use this in our distance analysis, right? Right? We can do that, right? So if I take the distance analysis, the union bound we had before, and transform it over to FQ, okay, there's a q minus 1 here, there's a q minus 1 here, and there's this AW, HQ, and Q. And then you get some awful, horrible fraction you have to try and bound. And we actually could not bound this for q greater than or equal to 4. If you kind of push in this quantity, and if you only look at the q terms, when q is bigger than 4, like some derivative becomes like huge and like it just blows up. So this didn't work. But the observation was that we were just naively applying the union bound like one does usually. We did the union bound over every possible vector, and that led to this blow up. We couldn't do that. And I can't get into all the details on how we get around it, but I'll give you some intuition. Rather than applying the union bound in one shot, what we did was say, okay, we can partition the set of events that make the minimum, to analyze the minimum distance in such a way that we can keep partitioning in this until we can split it into a set of events that depends on the field size q and a set of events that doesn't depend on the field size q. And what this allows us to do is once you have this set of a union of events that depends on the field size q, you can apply a truncated union bound, which just says the probability is 1, at most 1. And then what you end up with is this final distance bound, which looks a lot like the binary case. You just have another summation and then one more binomial, but intuitively, in the binary case, we had n to the 4 minus some constant, and now it's n to the 5 minus some constant because we have like one more summation here. Okay. So that's a very, very high level without any details of how we get to here. And finally, I'll conclude with some experiments. We have an artifact available. We have it implemented in Rust. We use the Spartan polynomial IOP, and we run with these parameters. So this distance was calculated not from a final Stirling bound, but from some midway approximation. And we just set the distance to be 1/10, and then, okay. And we do all this. So very quickly, you can see that we are slightly slower than breakdown, but we are comparable in proof size, verifier time, and opening time in the polynomial commitment scheme. The same holds for our SNARK performance. So again, we are the green line. And finally, just a quick note, we are in ECDSIA signature verification, we're comparable to breakdown in verifier time. Our proofs are concretely small, and we also have a slightly slower prover than breakdown, really taking advantage of the simplicity of the code. Okay, and this is again, this is what we show in this work, and thank you.
So we may have time for one very quick question, just while the next speaker is getting ready. Okay, then in the interest of time, we'll move straight on to the next talk. So the next talk is going to be Mangrove, Scalable Framework for Folding-Based SNARKs. And yeah, welcome Wilson, who is going to give the talk.
Cool. Hi, my name is Wilson Nguyen, and today I'll present Mangrove, our scalable framework for constructing folding-based SNARKs. This is joint work with my co-authors while at Stanford. Similar to the prior talks of this session, a SNARK consists of two parties, a prover and a verifier. The prover claims that knows of a corresponding witness such that this instance witness pair belongs to some relation. In order to convince the verifier, the prover can send a succinct proof much smaller than the witness, for which the verifier can read and output accept or reject. I want to highlight that crucially, both the prover and verifier in this model depend on a reference string that is generated during a setup procedure. This reference string will ultimately place some bounds on the prover and verifier operation, which I will describe shortly. What we need is SNARKs that are capable of scaling to meet the demands of modern-day applications. For example, the Filecoin network produces over 560 trillion constraints every day. And in order to prove this number of constraints, they have to produce 6 to 7 million individual SNARK proofs, each covering around 100 million constraints. Now, this 100 million is actually an upper bound placed by the size of their reference string. Furthermore, even simple operations in verifiable machine learning, such as a matrix multiplication, can take around 700 million constraints. So clearly, we need SNARKs capable of handling very, very large statements. So what's preventing SNARKs from actually scaling to this size? Well, the main barrier is proving memory. SNARKs such as Plonk, Marlin, Groth16, and STARKs use algorithms such as FFTs and proximity tests that often enforce linear memory requirements. In practice, this amounts to the use of machines that use terabytes of RAM. However, there have been recent SNARKs which try to address this memory concern, in particular, the design of streaming provers, and also distributing the RAM requirement across multiple machines. However, as I alluded to earlier, these SNARKs suffer from a key drawback. In particular, the size of the constraints that they can prove is upper bounded by the size of their structured reference strings. To date, the largest structured reference string generated by Filecoin is only 2 to the 27 in size. This is around 130 million, and is far below the amount of constraints needed for the applications I just mentioned. The reason why it's so difficult to produce such large structured reference strings is because they require expensive and hard to coordinate setup procedures, where simple mistakes can be disastrous. That's where our work comes in, Mangrove, a SNARK that is capable of proving an arbitrary number of constraints not bounded by a structured reference string, has transparent setup, which means we don't need the difficult setup ceremonies, can run on minimal hardware, has a memory-efficient streaming prover, and with support for distributed proving. I would like to give a brief overview of the techniques we use to construct Mangrove. The computational model that we target is circuit satisfiability. Our first technique is the construction of a uniform compiler, which can reduce the task of proving circuit satisfiability for an arbitrary and large circuit, just proving that a series of small and identical chunks satisfy some local and well-structured global constraints. Our second technique is a new folding scheme for polynomial relations, which is capable of reducing the task of proving that all these small chunks satisfy their own local constraints, to just proving that a single chunk satisfies some local constraints. And finally, by combining this new folding scheme with the framework of proof-carrying data, we'll be able to recover a succinct prover. In particular, in the prior step, we do not recover a succinct proof because the verifier would have to check every reduction step. So let's start off with describing our uniform compiler. Recall that we're targeting the problem of circuit satisfiability. So here I have a simple circuit which consists of only 3 gates. How can we actually encode this problem? Well, each gate takes in 2 inputs and 1 output. And together, these triples are the instance and witness for the circuit. We can encode the types of gates that each triple must satisfy by the use of a binary vector, particular 1 for multiplication and 0 for addition. And finally, we can indicate which wires are connected to each other by the use of a permutation vector, as I'll describe shortly. These vectors and this encoding enforce 2 types of constraints on the values. In particular, a gate constraint, which enforces that each triple satisfy a particular type of gate, and the permutation vector, which creates copy constraints. In particular, it checks that the value vector is invariant underneath the encoded permutation. So wires that are connected should belong to the same cycle in the permutation. If this is such, then we can enforce that these wire values are actually equal. So recall that the goal of the uniform compiler is to actually break down these global constraints into just a series of small and identical chunks. So one natural approach might be to chunk along the gate boundary. So for this small circuit consisting of 3 gates, this amounts to just 3 separate chunks. Of course, in practice, the size of these chunks will actually be tens of thousands of gates, but this is just a tiny example. So how do these gate constraints and copy constraints fare when we decide to chunk up the circuit in this manner? Well, the gate constraints are fine because they only require values that are local to each chunk. However, the real issue arises when we deal with the global copy constraints. In particular, to check these global copy constraints, we would require accesses that are cross chunks, and hence these checks are no longer local to each chunk. However, we observe that by using multi-set arguments, we'll actually be able to relax these sort of global accesses. In particular, in a multi-set argument, the prover can pre-commit to their wire values and send this commitment to the verifier. Then the verifier can reply with some randomness, and now the global accesses are simply reduced to the following new global constraints. In particular, the verifier must check that the product of some locally computed products is equal to 1, where importantly, each local product only depends on the verifier's randomness, as well as the values located in each individual chunk. And finally, the multi-set argument also introduces another global constraint. In particular, the verifier must recompute the commitment that the prover sent in the first message to indeed confirm it's a valid commitment. But what we can observe now is that these global constraints are actually very nicely structured. So what we discuss is just our uniform compiler, which is able to reduce the task of proving circuit satisfiability for an arbitrary circuit to now just a series of small local constraints and global constraints for a bunch of chunks. And so now we'll move on to how we can use folding schemes for polynomial relations to reduce the task of proving these global and local constraints. So at this stage, we'll actually not recover a succinct argument, but we'll describe shortly how we can. So just to recap, we have some global constraints that were introduced by the multi-set argument, as well as some local constraints that must be checked for every single chunk of values. For now, let's just focus on the local constraints and also just a single chunk. These local constraints are purely just a vector of values and also a gate check and a local product. We observe that applying a linearly homomorphic commitment scheme, such as a Peterson commitment scheme, will actually be able to translate checking these local constraints to purely just checking that an instance belongs to a polynomial relation. In particular, this gate check and local product get reduced to just checking if some polynomial map F evaluates to 0. Why did we care about this transform? Well, polynomial relations have a very nice structure. In particular, they can be batched using a folding scheme. So what does that even mean? Well, let's consider multiple chunks this time, where we want to prove their local constraints. We can reduce the claim that multiple instances belong to this the language of this relation by the use of a folding scheme. In particular, given advice from the prover, the verifier can perform some simple homomorphic operations and produce a new instance. And now, if the verifier is able to confirm that this new instance belongs to the language, then with high probability, the original instances must belong to the language. So, zooming out, let's consider all the chunks. We can now batch the proving of all of these chunks to now just a single chunk. In particular, the prover will first commit to all these chunks and send them to the verifier. And then the prover and verifier can work together to reduce all these chunks down into a single chunk. And now to check all these local constraints for all the chunks, they simply have to just check whether the final chunk belongs to the language of this relation. The prover has a very simple proof for this. It can just send the corresponding witness, which is just the openings of these commitments. And the prover can check that it belongs to the relation themselves. So now let's focus on the global constraints that were introduced by the multi-set argument. In particular, there is a global product that the verifier needs to check that is equal to 1. Well, in a similar recursive manner, the verifier can just check this by aggregating the products in a tree-like manner. And at the end, we can just check if the root product is equal to 1. Similarly, for the verifier to recompute the commitment, we need some commitment that has a nice streaming structure or recursive structure. And so we can always leverage the classic Merkle commitments. To recompute this commitment, the verifier can simply just recompute it by taking hashes at every node in the tree. And at the very end, it can just check if the root hash is equal to the commitment that the prover sent in the first message. So altogether, we've now reduced these global constraints and local constraints for all these chunks in a tree-like manner, such that at the very end, the verifier just has to confirm, is this product equal to 1? Is this commitment the commitment that the prover originally sent? And do these commitments belong to the polynomial relation? However, there is a huge caveat. This is not a succinct argument because the verifier has to participate in each one of these reduction steps. And also the prover sends all these commitments to the verifier. So it's not a succinct argument, but it has a very nice recursive structure. And that leads us to our next technique. In particular, by combining folding schemes with the framework of proof carrying data, we're actually able to recover succinctness. In particular, proof carrying data allows us to generate cheap and incremental proofs that attest to the verifier's checks at every step. And so the prover can attach to every node a proof that they've generated this instance appropriately. And that's it. That's actually just our mangrove proof, along with the opening, which is necessary to check if the commitments belong to the polynomial relation. Of course, I've omitted a lot of details related to the subtleties of knowledge soundness. I've also omitted optimizations for the recursive proofs and also to minimize the number of constraints, but you can just check out our paper for all the gory details. Now I'd like to discuss how this allows us to immediately recover a streaming algorithm. In particular, we can observe that all nodes of this tree within the same layer are independent of each other. So we can just produce these incremental proofs and then forget about the nodes we don't care about anymore. And that is how we generate the proof in a streaming manner. But I just want to state that this is not just a theoretical construction of a streaming prover. This is actually concretely efficient. In particular, we estimate from micro benchmarks that the mangrove prover can run at an order of magnitude faster than the latest streaming SNARK, all while using a little bit less memory. In fact, it can actually be competitive with some non-streaming transparent SNARKs. The one caveat is that the mangrove proof size is quite large. However, it has a very nice structure where it's amenable to compression by a transparent SNARK called Spartan, which adds only a minimal amount of time to the overall proving time. In particular, for all the parameters we considered, it only took less than a minute and resulted in proof sizes for all parameters that are less than 14 kilobytes. So the takeaways of this talk are that the uniform compiler bridges the gap between arbitrary circuits and repeated computation. Leveraging the framework of proof-carrying data allows you to generate proofs with low memory for repeated computation. And our conceptually simple framework can outcompete recent SNARKs, all without being bounded by a structured reference string. Cool, thank you.
So we actually have plenty of time for questions now, if you want to step up to the mic.
Thanks for the great talk. So in your current SNARK, you use the arithmetization that's like Plonkish, you have gates and you have copy constraints. Did you think about other kinds of arithmetizations like RONCS?
So for the simplicity of this talk, I only did explicitly circuits, but we consider a more general arithmetization in the paper that can do arbitrary custom gates. We haven't considered RNCS because I believe it requires a different type of streaming input.
I see. Thanks.
Any more questions? Maybe I'll ask a quick question then. When you applied further proof systems at the end to compress the proofs from Mangrove, did you have to put significant effort into compressing the constraint systems involved in Mangrove to feed them into the other proof systems, or was that were they already sort of good enough to achieve this kind of performance?
So a similar strategy was used in the NOVA paper. In particular, since our witness is just committed using a Peterson commitment, it can immediately be interpreted as a multilinear commitment. And so Spartan just almost immediately applies.
I see. Thank you very much. Well, then let's thank Wilson again. Okay, so now we'll move on to the very last talk of this session, which is Hypernova, recursive arguments for customizable constraint systems. And the talk will be given by Abhiram. Please go ahead.
Thank you, Jonathan. Okay, let me just check that this works. Great. All right, so I'm aware that this is a talk right before lunch, so I'll try to keep it short and sweet. So yeah, I'll be giving a talk about Hypernova, or recursive arguments for customizable constraint systems. It's a joint work with Srinath Sethi. So the goal for today is to design practical ZK SNARKs for recursive computations. And what I mean by this is that we want to design a proof system that allows us to prove statements that claim that a non-deterministic function f applied n times to some initial input z0 results in some output zn. And I say non-deterministic because this function f should be able to take some additional secret witnesses along the way. Okay, so it turns out that such a computation actually captures many applications of interest. Now, for example, if f is a delay function, then such a proof system immediately enables verifiable delay functions. And alternatively, if f validates blocks of transactions, then we can get something called a ZK rollup, which allows us to quickly verify large chunks of updates to blockchains. But perhaps the most exciting recent application is this idea of a zero-knowledge virtual machine. And the core idea here is that we can let that function f represent an entire CPU. And as such a proof system enables us to prove the correct execution of an entire virtual machine. So the traditional approach for achieving such a proof system is to just take that function f, unroll it as many times as you need into a giant arithmetic circuit, and then use the best available SNARK to prove the correct execution of the circuit. But exactly as Wilson was saying, one of the key limitations of this approach is the memory overheads. Because of how SNARKs today are designed, the prover memory will scale linearly with the entire trace of the computation. You can imagine for applications such as virtual machines, this is a little too expensive in some cases. Now, as a concrete example, Jolt, which is a state-of-the-art proof system which uses this approach, can prove 17 million cycles of RISC-V in just 125 seconds. But to do so, it requires a machine which has 512 gigabytes of RAM on board. So to get around this memory-based issue, modern approaches, including Hypernova, use an approach known as incrementally verifiable computation. And the core idea with IVC is that we can run a single step of the function f and then locally write a proof for the correct execution of that single step of the function f. And later, as the computation proceeds, as we unfold and run more steps of the function f itself, we can correspondingly update the proof alongside such that this proof talks about the correct execution of the computation up until that point. Now, the core requirement of IVC is that as we unfold this computation and as we update the proof alongside, the proof does not grow in size over time. And this is the key requirement that enables us to say that the prover memory overhead only scales with a single execution of the function f rather than the entire computation trace. Okay, so there are several key approaches to achieving incrementally verifiable computation. The original approach, due to Valiant back in 2008, is using direct recursion. And the core idea here is that, well, in each step, instead of proving just the function f itself, instead we can prove an augmented function f prime represented as a circuit. And this augmented function, in addition to running the original function f, also runs a SNARK verifier, which checks a SNARK proof of I iterations of the function f prime. Well, now what we can do is write a new SNARK proof, pi I plus 1, which attests to the correct execution of this latest iteration of the function f prime. And effectively, this proof pi I plus 1 attests to the latest iteration of the function f, as well as the existence of a SNARK proof for all prior iterations of the function f prime. And as such, this proof pi I plus 1 is effectively a proof for I plus 1 steps of the computation. Now, the magic here is that we've converted a proof of I steps into a proof of I plus 1 steps while ensuring that this proof does not grow in size. And moreover, we have that the prover memory overhead is only scales with the size of this computation f prime, which is fixed. Okay, so while this approach is incredibly elegant in theory, as Ben-Sasson and others showed, unfortunately, in 2014, it turns out that proving and verifying an entire SNARK per step of recursion is concretely expensive. And really, this boils down to the fact that the best-known SNARKs use pairings, which in this particular case would blow up the recursion overhead. In this particular case, the recursion overhead is all the additional gates you need to represent a computation f prime on top of the original function f. And you can imagine a SNARK verifier that uses pairings, you'll have to start representing these pairings using just addition and multiplication gates, and that blows up very quickly. And the other key issue with this approach is that to instantiate in the recursive regime, we need to start using something called cycles of pairing-friendly curves, which are 10 times more expensive than standard alternatives. So to get around the concrete costs of direct recursion, in 2019, Baugrig and Hopwood introduced a fundamentally new approach, now dubbed accumulation. And the core idea here is that, well, let's not verify the entire SNARK per step of execution. Instead, let's only partially verify it, and then compress the rest into something called an accumulator. And this accumulator is designed in such a way such that you can compress as many SNARKs as you'd like into it, but it still does not grow in size. And moreover, we have that checking this final accumulator is equivalent to checking all the prior SNARK proofs that were compressed into it. Now, the core benefit of this approach is that we no longer need hyper-optimized pairing-based SNARKs. And as a result, we no longer need to rely on cycles of pairing-friendly curves, which offers almost an order of magnitude improvement. And now this brings us significantly closer to modern practical IVC. But the key limitation here is that the prover still needs to produce a SNARK in every step of execution. And moreover, the recursion overhead the recursion piece still needs to partially verify the SNARK, which is still concretely expensive when you consider that this must be done using a bunch of addition and multiplication gates. So this led to the modern approach of folding, where we realized that, well, you don't even need to partially verify a proof. Instead, you can design a new procedure known as fold, which can compress two of these proofs entirely. And the core idea here is that, well, we can have a proof for the prior step of execution, we'll call that pi I, and another proof for all prior steps prior to the last step of execution. We'll call that capital pi I. Okay, and what we can do is run this fold procedure, and this will take two proofs of the same size and compress it into a single proof of the same size that can be checked in place of the two original proofs. Okay, so the core realization with this architecture is that we don't even need succinct proofs anymore. Okay, and what we showed in Nova 2 years ago at Crypto 2022 is that effectively this allows us to whittle down the prover cost per step to just 2 multiscalar multiplications, which is a significant improvement over having to produce an entire SNARK per step, which is roughly around 10 multiscalar multiplications. And moreover, we show that the recursion overhead itself can also be whittled all the way down to just a constant number of group operations and hash operations. Okay. So now, while folding-based IVC schemes have shown promise in the last 2 to 3 years, as we start to use them to build various applications, we're starting to discover various growing pains. And the chief of which is that prior to Hypernova, there were no efficient methods for folding high degree constraints. And what I mean by this is that prior folding schemes were designed around R1CS, which is a quadratic constraint system. And by extension, this means that we can only represent the IVC function f using quadratic constraints. And while technically any computation you want can be represented using just quadratic constraints, ideally for certain computations, you'd like to support higher degree constraints, such as degree 3 and degree 4 and degree 5 and so on, because that could be much more efficient for certain types of computations. Okay. Now, the second core limitation is that prior to Hypernova, IVC is limited to just running the same function over and over again. And for certain applications, such as verifiable delay functions, this is perfectly reasonable. But for other applications, such as virtual machines, we might want to envision a scenario where each recursive step can dynamically schedule a new function to be run in every new step. Okay, and in the particular case of virtual machines, this could correspond to, say, dynamically scheduling a new instruction to be run in the next step. Now, the third core limitation is that currently zero knowledge is quite expensive to achieve because there's only 2 known methods. The first is doing per step overheads, very expensive per step recursive overheads. And the other is to use proof indirection, where you write a ZK snark about the existence of a valid IVC proof. And both of these approaches are not as efficient as we could make them. And the final core limitation is that when you go and try to instantiate all of this over a cycle of curves, the current blueprint we use is based on the approach of Ben Sasson and others back in 2014. However, that blueprint is closely based on SNARK-based IVC schemes. And ideally, in this new regime of folding-based IVC schemes, you want to find a new way of instantiating these cycles in a way that takes advantage of the structure of folding schemes. So Hypernova can be viewed as addressing each of these challenges one by one. In particular, we start off by designing an efficient folding scheme for high degree constraints. And in particular, we design a folding scheme for customizable constraint systems, originally introduced by SETI and others back in 2023, which generalizes R1CS to higher degree constraints than degree 2 constraints. Okay. Now, the second core contribution of Hypernova is that we introduce a new primitive and construct a new primitive known as non-uniform IVC, where precisely it enables us to dynamically schedule a new function in every step of recursion. And this allows us to capture more dynamic computations in the case of IVC. Now, the third contribution is that we show that we can use folding schemes in a new way to blind the final IVC proof by folding in randomized terms into the IVC proof. And this gives us a much more efficient way to achieve zero knowledge, where you just do a little bit of processing at the end of the entire computation instead of having to deal with computations throughout the entire IVC process. And finally, we introduce a new methodology known as cycle fold, which gives a much more efficient way of instantiating folding-based IVC schemes over cycles of curves. Now, Hypernova can be viewed as the combined total of all of these contributions. But today, I want to focus on the first contribution, which is designing an efficient folding scheme for high-degree constraints. So recall that our goal is to fold proofs about customizable constraint systems. So our core technique here is that what we'll do is we'll design a folding scheme that allows us to prove a proof or fold a proof about customizable constraint systems into a running proof about linearized constraints. That is, only considers the linear part of the constraints of CCS, and we'll call that LCCS, okay? And the core idea is we take these two proofs as input and compress them into a new proof, pi prime LCCS, which is of the same size as the original linearized CCS proof, but can be checked in place of both the original proofs. Now, the core idea of our folding scheme is that we can use the powerful sum check protocol to take the original CCS proof and linearize it. And once we linearize it, or linearize all the checks you need to do to check that proof, then you can just use a standard linear combination to compress it or fold it into the running linearized CCS proof, okay? And indeed, what we show is that by using this approach, we achieve a minimal recursion overhead with just one group scalar multiplication when compared to Nova's 2, and moreover, just requires a logarithmic number of hashes. Okay, so now I want to give a quick technical overview of how we design such a folding scheme. So we'll start off with a proof for CCS as well as a proof for linearized CCS, okay? And the core observation is that, well, checking a CCS proof is roughly equivalent to checking a high-degree polynomial Q is equal to 0 on a fixed set of points. And similarly, checking a linearized CCS proof is equivalent to checking a set of multilinear polynomials, L1, L2, L3, and so on and so forth, on a single random point R1 is equal to a set of values V1, V2, V3, and so on and so forth. Okay, so really, we're asking a question about evaluating many different polynomials on many different points. So our first observation is that, well, you can reduce this to a task of checking just a single polynomial G. And the way you do this is that you encode evaluations of the Q polynomial and evaluation of the L polynomials as Lagrange coefficients into this giant polynomial G, okay? And then using a random linear combination, you can reduce this to a task of checking a sum of evaluations of this polynomial G is equal to some particular value V. Now, for those of you who are familiar, just cleaning everything up, really this reduces to just asking the familiar sum check question, where you're asking, well, taking a polynomial G and summing up all its evaluations on a particular domain, is that equal to V, okay? Now, at this point, we can use the famous sum check protocol to reduce the task of checking a sum of evaluations to the task of checking the evaluation of G on a single random point. Okay, so we've reduced all the way from checking many different polynomials on many different points to checking a single polynomial on a single point. And now our core observation is if we take a deeper look at G and we open it up and look inside, what we'll see is that really evaluating G is equivalent to evaluating two sets of multilinear polynomials, which I've denoted in blue and red. Okay, and what we see on top of this is that these two sets of multilinear polynomials roughly have the same structure, that is, have the same underlying polynomials in terms, okay? And moreover, we have that these two sets of multilinear polynomials are being evaluated on the same random point, okay? So taking advantage of all of these facts, what we can do at this point is just take a random linear combination to reduce the fact of checking, or the question of checking these two sets of multilinear polynomials to the task of checking just a single set of multilinear polynomials on the same random point. So this is the core compression step internal to the folding scheme, okay? So now the magic is that, well, when we started, I said that, well, checking a linearized CCS proof is equivalent to checking a set of multilinear polynomials on the same random point. Well, through a series of reductions, we reduced all the way down to checking, again, a set of multilinear polynomials on the same random point. So what we can do at this point is repackage this up as a linearized CCS proof and then output that as a result of this folding scheme. So this effectively concludes our folding scheme. We reduce the task of checking a CCS proof and a linearized CCS proof into a task of checking a new linearized CCS proof that's of the same size. So with that, I want to pull back up and summarize the key contributions of Hypernova. First, we design an efficient folding scheme for high-degree constraints, in particular customizable constraint systems. And then what we show is that this implies an IBC scheme that allows us to represent the IBC computations themselves using higher degree constraints than just degree 2 constraints. This is applications in various scenarios where the computation itself can be much more efficiently represented using high degree constraints. And moreover, on top of that, we show that this can be extended even further to the setting of non-uniform IBC, where you can design computations that can dynamically schedule new functions to be run in every step. Okay. And then we show that we can use folding schemes in a new way to achieve zero knowledge by blinding the final IBC proof. And finally, we introduce cycle fold, which allows us to instantiate everything we've developed over a cycle of curves much more efficiently than prior approaches. Thank you.
Any questions about Hypernova for Abiram? Okay, then maybe I'll just ask a generic question. So what is still the remaining bottlenecks, and how do you think this could be improved even further?
Yeah, so that's a great question. So as we're seeing, a lot of folding schemes are chipping away and making it faster and faster and better. You can see that Hypernova has a logarithmic number of hashes, and people are working towards making that a little bit better. So that's one of the major questions. How can we make these folding schemes faster? And also there's a lot of questions about, how can we actually specialize IBC schemes and similar schemes to applications such as virtual machines? Like, what are the challenges there? So these are, I guess, 2 open directions.
Thanks. Any other questions about Hypernova? Okay, if not, then let's thank Abiram and let's thank all the speakers from the SNARK session again. Lunch.